Hello, everyone. My name is Olena. I actually live here in Berlin, and I don't like sunny days. I like this perfect Berlin weather where we have rain and gloomy weather. But anyway, I work with a lot of data. And today, during this session, I wanted to talk about the topic which has been fascinating me for quite a while: anomaly detection. And the rough plan of what we are going to see today would be, we will talk about anomaly detection in general terms, some types and flavors of different anomaly detection, and also how this affects the tools which we are going to select. Then we will talk how, again, the overview on the solution within the anomaly detection fields, and in particular about a couple of models. First, we will talk about ARIMA, its history and how it works, and then we will talk about a different model, LSTM, and also why we need to forget certain things to have a better memory for the rest. I do see my screen, and that's why I was very sure you see it as well, but you don't. Okay, anyway, this is the plan. You just missed one slide, which was not super important. So we will be talking about ARIMA, about LSTM, and then we will talk also what should you use and when. Generally, anomaly detection is all around us. Let's imagine we work at a company that builds navigation systems. Actually, I worked in one here in Berlin, and that was in the past. But anyway, so our products is installed across the cars that move around the cities. And we kind of recommend the best routes for the users, for the drivers in those cars. And every now and then, a driver decides to take a different route than the one which our system recommends. Maybe they prefer some scenic tour, or they just know a shortcut. Whatever the reason is, it's not yet an anomaly. But then another driver makes same decision. And then another drivers make a decision, and still, is it anomaly? Maybe not. Maybe they follow some seasonal patterns, and they might be avoiding some roads during, I don't know, like school drop-off hours. So maybe nothing to worry about yet. But soon you notice that almost all the drivers are not using that recommended tool. And that's when you start asking, is there an issue? Is there a construction? And I mean, for Berlin, we know constructions pop up everywhere. Is it an accident? Should we alert other drivers? Should we actually follow and then figure out what is happening and when that road is free again? So anomaly detection helps us to recognize those unanticipated shifts in the behavior of people, whether it is road traffic, server performance, maybe financial transactions. And here I Googled, and there is almost $40 billion are hidden in the fraudulent transactions using the credit cards. And we definitely want to prevent those. Then there is IoT devices which send the data. So whatever we have in all the objects around us, we often try to detect anomalies and prevent those anomalies. So if we would have to give a definition to anomaly detection, it would be looking for some observations or events which are kind of deviate from what we consider to be a usual behavior. And they're inconsistent with the rest of the data set which we have. And we work with a lot nowadays with data, so we have huge amounts of data. And at this point of time, we can actually split anomaly detections into two groups. Quite simple. So we have unintentional anomalies and intentional anomalies. So unintentional anomalies, those are usually due to some kind of error. Either the processing or error, or maybe like human error, sensor or hardware, data transmission issues, or any other things. Those they still bring some dirt into, some noise into our data, and we obviously want to avoid them and clean up before we use the data downstream for our decisions. But usually we don't really care about so much about it, and we only alert if this kind of unintentional anomalies repeat or create some kind of a pattern. Then there is intentional anomalies. Those we are really trying to prevent, because those are meaningful deviations from the norm due to some kind of deliberate actions or events which are happening around us. It can be something very negative, as a fraud or financial manipulation, or cyber attacks, for example, some brute force logins or something else. It can be something actually totally innocent, which might be not really bringing any troubles. For example, during the holidays, more flights are sold, or there is a product launch spike, or anything else. So maybe those anomalies are not evil, but maybe they are. Then, so with those anomalies, we can also divide them differently. And this will be important for us also to think what kind of tools we can use later to figure out if there is anomaly or not. So we have the point anomalies. That's probably the easiest type of anomalies. These are global outliers, some individual data outside of the rest of the data set. Those usually can be, again, like error or noise, or some unique occurrences, or something more evil, for example, or potential evil. For example, in your bank transactions, a huge amount of money was taken comparing to the rest of the transactions you have there. Whether it is like you have done it or someone else, that's depends on what we later do with that anomaly. Then we have contextual anomalies. This is where the data deviates from a specific context. For example, it's not necessarily that the outliers, when we consider those dots in isolations, they might be still fit in the picture. But when you view it within the specific context, you might be seeing that there is an issue. For example, the home energy usage spike during the midday, when usually none of your family members are at home. And I'm not sure, maybe the cat is watching too much TV, or maybe there is some other issue. So then we want also to look at those. Then we have collective anomalies, where they together deviate from the norm, even though maybe like individual, again, instances are considered to be normal. And this is, for example, a search in the traffic from multiple IP addresses at the same time. And then it's like, okay, maybe there is something here, there is a pattern. So we will come back to those when we will be looking at different solutions and what kind of approaches we can apply to these problems depending on the type. Then for finding the anomalies, we are not really using a crystal ball. Not yet, but we are using what we call a predictive analytics, and it relies on the historical data which we have, and it is used together with statistical modeling, data mining techniques, and machine learning. And there are different ways how we can approach the predictive modeling. We can use statistical supervised models which rely on the labeled data set. It's where we train the model, we give some information, what is anomaly, what is not, and then those models help us to determine whether the new instances are anomalies or not. We can also rely on unsupervised learning. It's where the model itself tries to classify the data into different groups, anomalies, not anomalies, or other chunks of data. However, for us, we are going to look into the third group of these models. We are going to look into time series models because the streaming data is often the time series data. So whether we are using the data coming from the transactions or the cars or IoT devices, this data is kind of unique because we measure here one or more variables changed over time, creating some dependencies between the data points. So each data point actually somehow relates to the previous data points in the sequence. And this impacts the choice of the models which we do and what kind of solutions we can apply. So for time series anomaly detection, there are different tools which people use. Visualization, we are not going to cover it, but it's actually pretty widely used to spot those patterns by visualizing them. Then there are statistical models, and there are machine learning models. And we are going to look into statistical and machine learning models for the time series anomaly detection. And we'll start with statistical models. And they are quite intuitive and easily kind of understandable by what results they bring us, which is why they actually are quite widely used in the practice and also in the industry. So statistical models, they rely on mathematical formulas or mathematical models to use the predefined thresholds based on historical data patterns. So it's more about math here. Still, we can do quite a lot. And going from the most simple use case, for example, we can use what is called the 3 sigma rule. This is a simple threshold rule. And we can define, for example, you are looking at the data for a particular user who makes payments with their credit card, and it's like a question: is 300 euro payment anomaly or not? I mean, it will depend on a user. And how exactly we are using this 3 sigma rule here? We are taking this mean daily spend mu. For example, it can be, okay, these numbers may be too low, but 100 euros per day for that person. Then we actually calculate the standard deviation for the payments by the same person, and we calculate this threshold, 3 sigma. And according to this formula, it will be 220 euros per day. So our 300 euros is higher number than that, so we can flag it as anomaly. Whether we need to act on it or not, that's a different question. But the logic behind this is that according to this formula, which is quite simple, but still, we believe that 99.7% of data should be within this 3 sigma value. And for us, the 300 euros is not within 220 calculated 3 sigma value. So it's outside based on the information which we know from the spanning by this user. Similarly, we have some other formulas. So this is another one, Z-score based detection. For example, if you want to detect is 11 transactions per day by a given user's anomaly or not, we can also use a formula which calculates Z-score. So it takes the X, which is the value, the transactions count for today, which we are evaluating. Then we take the mu, the mean daily transaction count, and sigma, the standard deviation. And then the calculated value, again, we have this 99.7%. So if the Z value will be within -3 and 3, so this is more or less where we expect the bunch of our values based on that sequence. And if it's within -1 and 1, this is actually maybe like even more central. It's also kind of a good value for us. And then if we do a calculation based on some numbers, so here the mean was 5 and standard deviation calculated 1.5. This is like imaginary numbers for imaginary human being having 11 transactions per day. But for that human being, that number of transactions is unusual based on the history. So we can say that we detected an anomaly. But this is quite simple rules. This is pure simple math. What we can also increase, again, statistical models, we can actually use something more complex. We can use what we call forecasting models. This involves moving averages, RIMA, which we will talk in a second, Holt Winters, and other different models which are somehow a bit more complex when you look at the math. But in general, how it works, we try to predict the behavior Here, just like this simple sequence. But we try to predict the behaviors, and we look at the actual behavior, and we compare it to what we predicted. And then we look at the delta, so the difference between the actual behavior and predicted one, and we compare it to the threshold which we established. And based on that, we see where the numbers which were in actual behavior significantly deviate from our prediction based on the established threshold. And those numbers are our anomalies. So this is how it kind of works. There is more magic to that. And as an example of those statistical models, let's look at the model which is called ARIMA. It stands for Autoregressive Integrated Moving Average. It actually consists of 3 different parts, and I must admit that for me the name is not super logical, but let's go one by one, and I'm not even going so deep into the math here, even though I think that those formulas I copied were correct math for those parts. But we are not going to look into the math itself, we are instead going to check the history and kind of maybe the logic behind those parts in this model, because the history goes quite far into the past. And starting with autoregressive part. So autoregressive part, and I like this part because actually it's connected to the sun. So George Udny-Yule, the British statistician, back in 1927, he was looking at the problem. At the problem where actually a lot of scientists were paying attention to that problem already for a long time, that on the sun we have some spots. Those spots are coming and going with a cycle of 11 years, but it's really like a rough cycle, not really something at that point of time was kind of a question, is it really a cycle or not? Is it a pattern? And at that point of time, when we were talking about cycles, we were talking like, for example, a day, it's like more or less 24 hours. We established it repeats, so we can rely on that, or a year. But that particular one, it was like, yeah, it's around 11 years, but it's not really 11 years. So then you'll try to find a mathematical way to model this kind of noisy periodic data. And he managed. He created a model which tries to predict the value depending on the previous values. And it was a kind of a start for this autoregressive model, and actually was kind of a big deal at that point of time. So autoregressive, using past values to predict the future, even if it's imperfect, even if it's kind of the cycles don't match each time each other. Then moving average. Moving average was actually kind of the start for the moving average model was brought by Eugen Slutsky. Same year, even though it didn't become like well known till maybe 10 years later. But Evgeny Slutsky, he showed if you take random shocks in your data, totally like which looks to the human eye randomly, like sudden changes in consumer behavior, weather, at that point of time, wars, whatever. And if you smooth them over time using a moving average, you get something that looks like a wave. So something which looks way smoother and way kind of more cyclic. And so we can make order out of chaotic data if we use the right filter. And here, what we want to do actually, to use moving average not over the data itself, but over the averaging the past error terms. So we are actually using the moving average over the mistakes which are done when calculating, trying to predict the future values. So, because errors which we which we make in the prediction of the future values, they also have patterns. So this moving average is mostly like to focus also on the past mistakes to improve the future guesses. And now the third group of scientists, they try to combine these different models, which is like autoregressive moving average. They are two different models, and they tried to integrate them together. It was like these two guys, and they tried to unify the models and create the method which allows to use those models together. And that actually was Box-Jenkins method, and that is actually basis for ARIMA model. But they had a problem. They had a problem is that those models work only well with stationary data. And now the question is, what is stationary data? And this is a bit maybe too much of a math, but still. So stationary data, so let's first talk about non-stationary data. Non-stationary data is usual data. It's like, for example, your transactions over the day or the movement of the stock market. So you actually get the stock market data, kind of you have some patterns up and down. And I mean, like someone tweets something and then the whole market goes down. So there is kind of a lot of movements there. We actually want to eliminate that movement. We want the data where the mean stays around the same level. So we want to lose maybe that precision of the data, those spikes and downs, and we do it with the differencing. So we apply differencing of the data. So instead of looking at the values, for example, for the stock price themselves, we actually look at the difference between this value and the past value. And then we calculate the difference, and that allows us to flatten the line and to have a more meaningful prediction when using those other models. So we remove the trends. We do lose some data at that point of time, but for ARIMA, we don't care about those details, what was the value of the stock on that given day. We actually only care about the differencing which we see and kind of how the price was changing day to day. So this is ARIMA. We'll come back to that in a second, how to apply it. Now I wanted to say a couple of words of real-time streaming data. So we get a lot of values from different sources, for example, IoT devices, maybe social media, maybe microservices, whatever you have. We want then later get that data into some shape of maybe like dashboards or alerts or anything which allows us to work with real anomaly detection. So in this particular solution, together with the ARIMA model and other models, I'm going to use also a couple of technologies for data streaming. So first one will be Apache Kafka. How many of you, by the way, are familiar with Apache Kafka? Oh, we have quite maybe like 90% of the room. Then we are using Apache Flink to process the data. How many of you are familiar? Oh, less hands. But did you know actually that Apache Flink was invented, developed here in Berlin? I think in the University of Berlin, Technical University. So we are going to use Apache Flink. I will mention a couple of words later about it. And we are going to use ARIMA, and then we'll send data to Apache Kafka topic again. So for those of you who are not familiar with Apache Kafka helps us navigate a lot of data between your systems or external systems, whatever you have. It's super widely used in manufacturing, with banks and transactions. So all systems which really need to move the data very, very fast, many of them rely on Apache Kafka. And Apache Kafka, you can think of it as a pipe where the data moves like a water, and then we can actually change the size of the pipe. We can add more producers and more consumers when we need to transmit more data, and the data is securely stored and also replicated there across brokers. So it's a very reliable system which is built for low latency and high throughput. So it's actually an amazing piece of technology. Then Flink. Flink is kind of also sits at the heart of real-time data platform, and it can work with unbounded streams, such as, for example, data which comes from those transactions or stock markets or IoT devices, but also it can work with historical values. such as databases or models or whatever you have. And then it can actually combine that historical data together with the real-time data to make the decisions and decide on whatever you want to calculate, and then send that to the, like in your pipeline, to the destination or whatever you want to do with that information. So a lot of decision-making potential here, and Flink is being used for many different applications at the moment. Now, coming back to ARIMA, and this is just a very short stop, there are different libraries which you can use, and here I selected Python, because most of those machine learning models, or like actually statistical models as well, they work very, very well with Python. Lots of different solutions. I actually used the PMD ARIMA because it was actually very easy to use and gave me quite nice results. So now let's look at how we can implement that with the set of the technologies which I mentioned. So for example, we have some stock values going to Apache Kafka topic. Then with Apache Flink, we read the data from the topic. Then we need to chunk it into the windows and process parts of the data as it comes. And run anomaly detection function using, here I'm using Apache Flink. We want also to train and retrain this model from time to time. Finally, we can predict the next values based on the model which we trained, compare the prediction to actual values, and send the results to another Apache Kafka topic. So this is more or less the simple flow which we can do. The magic goes into the anomaly detection function. And in that function, this is a bit of kind of Flink logic. So for those of you who are not familiar with Flink, it's just code. Flink can be used with SQL, with Python, with Java. There are different levels of APIs which we have. But here we just read the data from the source, and we process the data, and we send it into the sink. And the source of the data, we work with Apache Kafka here. We read the data from the topic, and then we send the data back to the topic. And the anomaly detection formula using that library generally works like this. So we check if the amount of data we have is within this training size of the data. If not, then we kind of still need more data to train our statistical model. We check also the conditions. So I here tried to train and retrain data on different types of intervals to find the most sweet spot, how often I need to train data. And then do the forecast and compare to the last value. And then send the data to Apache Kafka topic with the mark if that value is anomaly or not. So it's true or false. So this is ARIMA model, statistical model. Now let's move to LSTM model. The LSTM model is a bit different. It's somehow more complex, and later I want to compare also two of them to each other. So LSTM stands for long short-term memory. And the core idea is to remember important information for longer periods of time while forgetting what isn't really useful. So LSTM is kind of also, it's quite a widely used model for prediction problems. For example, we have a problem given a letter, the goal is to predict the next letter in the sequence. And here, if I would be going through the sequence, at some point of time, I think you will be able to predict once upon the time, you can predict what actually was there. So the prediction is kind of impossible without the context of sequence of the letters. And knowing the context, the next letter is easier and easier to predict as the sequence progresses long enough. And LSTM is designed for applications where there is an input. So the input is an ordered sequence, as in our real-time sequence data, where information from earlier in the sequence will be important to make the decision later. And LSTM is a special kind of recurrent neural network. In a basic recurrent neural network, each step in a sequence, like for example word in a sentence, produce an output and a hidden state. And that hidden state is passed to the next step, helping the network to remember previous information. But the problem with RNNs in the past, or actually also currently, is that they actually forget too quickly. So what we do in LSTM to solve that, we add a bit of a state so that we can have more long-term dependencies, and remembering kind of the start of the sequence when we already progressed quite long within that sequence. So we have a state in a cell, and the network can then decide whether it needs to update the cell, the state, or it needs actually like to add something there or to erase something from that state, from that memory. But how exactly it decides whether we need to remember more stuff or forget? And for this, we use gates. So we have input gate, which detects, so when we want to add a new memory, then input gate opens. We have forget gate, which actually opens when we want to forget something from our memory. And output gate, which decides if the information from the state should be actually used to generate the output. And each gate is kind of a smart filter. And those decisions which gates have to make, they actually are trained during this model training on a lot of data. And then the model will know when to open those gates and when to keep them closed. So for example, if the network would be reading a sequence like the cat, which was very small, sat on a desk, at that point of time, when it reaches the word sat, the model might actually be smart enough to keep the word cat, because that was important in the past. Even though the words cats and sat, they're quite close to each other, but the model is trained on that text to know that cat is an object in that sentence, so that we want to keep it. Even though like the rest of the words can be actually forgotten because they don't make much sense. So like any other network, LSTM is based on weights and biases, quite a lot of them, more than a usual RNN network because of those extra gates. And then the network is learning how to open and close those gates by training on a lot of different examples, which we have to provide. So LSTM in general is designed for complex patterns where earlier input matters a lot. So it actually fits for our use case as well. So we can train it on not only on textual values, but also on the mathematical values if we have a lot of data to provide it. Here, we can do it similarly how I did it with the ARIMA model using Apache Kafka. There is a bit of a difference in the approach. Training this model will be more expensive than training the statistical model. But we can read the data from Apache Kafka topic. We can process the data in Windows, run anomaly detection, and here we do something a bit differently. We actually create the sequences based on our data, and at the same time, we reconstruct the sequences using LSTM model. An LSTM model, we have to pre-train it in periodically, like in advance, based on our data, however you approach our data. So for example, I'm using Iceberg to hold the data, but you can pre-train the data, pre-train that model on the historical values. You will have to retrain again this periodically and read your historical data and prepare the model based on some kind of logic you have. And then we compare those reconstructed sequences to the created, and those anomalies then go back to Apache Kafka topic. For LSTM, we also have a number of different libraries in Python. which you can use, and then within, like you can save the model, you can kind of train the model on the data, you can later save the model, which is already trained, and then to make it accessible through Apache Flink. And the rest is kind of the same as I was showing with ARIMA model to get that information and to process it and bring the results back to Apache Kafka. And the example I was running was pretty straightforward with a lot of like values. The blue one is normal, and the red dots were an anomaly which I was detecting when I was generating the data. So now the question is, what should you use and when? And the thing is, anomaly detection is not one size fits all. So depending on the use cases, and here I'm coming back to those different types of anomalies which we have, and based on that, we can use different approaches. For example, for isolated outliers, we can use those very simple statistical thresholds, so those formulas with 3 sigma or Z value, which are calculated very, very fast, and then you can actually already at that point of time raise some issues if you see a huge deviation. If you have some seasonality or non-contextual patterns, you can use the forecast models. For ARIMA, for example, it has also a model which works with seasonal data, or in general there you have actually a kind of a patterns which you can detect with that model. And if you have more complex patterns, you might want to use more complex models going into machine learning world. And overall, both approaches, statistical and machine learning, they play important roles, and they often actually complementary. So statistical models, they are quite simple, and they are perfect for well-understood metrics, and they provide baseline monitoring which you want to get. And then machine learning methods like those clustering, classifications, or like whatever we have, they can handle more complex use cases. And if you have evolving patterns, which, for example, like you might still get those with statistical models, but in case you cannot, you can apply the machine learning trends. You can also kind of combine them. First apply statistical for like the baseline, and then for those nuanced issues where you are not certain, to go for machine learning, because machine learning will always be more expensive in the kind of calculations and training the model. And the current industry is trend is to combine those two. This is actually I think we are. This is actually where at Confluent this is example of the script which we use as a machine learning. Based on our expertise, we actually combine statistical models with some ML features. So we are using ARIMA model. We made it a first-class citizen in real-time streaming. But we also made a lot of bunch of ML tools around it to make it more precise. And this is kind of to combine the simplicity with a bit more power and abstract away the complexities of buffering, historical values, and so on. So this is what I wanted to show you using Kafka, ARIMA, LSTM, and Flink. Last thing, because so many of you raised also the hand for Apache Kafka, if you want to check your knowledge, we have this pretty cool certification, a data streaming engineer. It's free. You can also get some LinkedIn page if you want, but it's just like to check your knowledge on the streaming technologies, Kafka, Flink, and Iceberg. And that's it from me, and I guess we have a couple of minutes for questions.
Yes, we do. So thanks for your talk. Pretty interesting. Do we have questions already? Doesn't need to be about Kafka, but can we? Now everybody's surprised.
If not, I will be still here, so you can catch me after the session. Thank you so much for listening.
Thank you.